Welcome everyone. In this example, I want to look at a phase transition. There's maybe a phase transition that you are not that familiar with, or might be a bit different than what you are normally used to, what is the so-called phase transition is. Normally, phase transitions in your head would be between a solid and a liquid, or liquid and a gas, or something like that. But we also get phase transitions between in a specific so-called larger phase. So in a solid, you can have phase transitions between different crystalline phases. So this is an example of that, where you have sulfur solid, so sulfur 8, and it moves between two crystalline phases of itself. So from its rhombic phase to its monoclinic phase. But for our purposes, all you have to see this as it's sulfur going from one phase to sulfur in another phase, right? So it's a phase transition. And this phase transition has an associated enthalpy for the phase transition and an associated entropy for the phase transition, right? And then we're asked to do two things for this phase transition. The first is to estimate the Gibbs energy of the transition at 80 degrees Celsius and 110 degrees Celsius. And we need to discuss what that tells us about the stability of the two forms of sulfur at each of those temperatures. And then finally, we must calculate the temperature at which the Gibbs energy is equal to 0. In other words, where the equilibrium, the phase equilibria, exists in a perfect equilibrium. In other words, where both of these two phases are perfectly balanced. In other words, where both of them are present in equal amounts, right? So, and then discuss what is the significance of that temperature. So I've kind of given away what we're going to look at there, but I mean, you can think about that so long. So let's look at question A. So question A is all about how do we calculate the Gibbs energy's variation with temperature. And that's, of course, if you have the enthalpy of reaction, you can say the enthalpy of reaction is just minus temperature multiplied by the entropy of reaction. All right, and we have two different temperatures. So we must estimate the Gibbs energy of reaction at those two different temperatures. So we have 80 degrees Celsius, 80 degrees C, and 110 degrees C. All right, so the Gibbs energy of reaction at 80 degrees Celsius is, of course, equal to, so our enthalpy is given as 3.213 kilojoule per mole reaction. And then from that, we subtract the 80 degrees Celsius. Now, 80 degrees Celsius is 353.15 Kelvin. All right, and our entropy is 8.7 joule per Kelvin per mole reaction, and we want to put that into kilojoules, so that must be times 10 to the negative 3 kilojoule per Kelvin per mole reaction. All right, and then if you go through this calculation and you round to 3 significant figures, actually you can round to 2 significant figures because of the entropy, then you get 0.14 kilojoule per mole reaction. All right, so that's the first, that's at 80 degrees Celsius. So what about at 110? What is the Gibbs energy at 110 degrees Celsius? Well, I mean, same values, so I'm not going to write the units this time, I'm just going to put the values, minus, it's just the temperature that differs a little bit, so 383.15 multiplied by 8.7 times 10 to the negative 3, and if you round this to 2 significant figures, then you get 0.12 minus 0.12 kilojoule per mole reaction. So what do you notice? Well, at 80 degrees Celsius, we have a positive Gibbs energy, right? So at 80 degrees Celsius, we have a positive Gibbs energy of reaction. And when the Gibbs energy of reaction is positive, that means we have a reactant favored equilibrium. Right? And at 110 degrees Celsius, our Gibbs energy of reaction is less than 0. So that means we have a product favored equilibrium. So I think actually, because this is a phase transition, we're looking at a phase transition, this would be best described actually by looking at it as such. It's not really a reaction. Look at it as a phase transition. So look at that as an equilibrium. And now look at this question as such. To say, right, so at 80 degrees Celsius, our situation is favoring the reactant side. So that means, what do we actually have? What is the stable form? So meaning we mostly have the reactant. So mostly what we have, let me just get that back in red. So that means the thing that we mostly have is the so-called S8, the reactant, the so-called S8 rhombic. And when we increase the temperature to 110, we have mostly the products. In other words, we have mostly the S8 monoclinic. All right. So, and that is exactly what the question is asking us about. What does it tell us about the stable form at these temperatures? So therefore, at 80 degrees Celsius, this is the stable form. Why? Because it's the species that is in excess. It's the species that's existing. It's a reactant favored equilibrium because it is thermodynamically the favored species. It's the species that wants to exist. It's exactly the same if you want to put it in a different perspective, like water. What is the favored phase of water at 80 degrees Celsius? It's liquid water. What is the favored phase of water at 110 degrees Celsius? It would be water vapor, right? So, and that makes sense. You'll have, at 110 degrees Celsius, you won't have liquid water. You'll have water vapor. And at 80 degrees Celsius, you'll have liquid water. So, and it makes sense, so hence that your equilibrium would be reactant favored for liquid water at 80 degrees Celsius and product favored for water vapor at 110 degrees Celsius. And that's just what this equilibrium is telling us. It's telling us that at these different temperatures, the one species is more stable. In other words, the equilibrium favors it because it is the stable species at that temperature. All right, so in other words, the rhombic form is the stable form at 80 degrees Celsius, and at 110 degrees Celsius, the monoclinic form is the stable form. All right, so I think that is quite significant. It's a very good application. It shows quite high level insight. This is a very nice question that tests your insight. A bit higher level than, because you might not know the sulfur that well, but it's a very nice way to look at this kind of problem. All right, so now keeping this in mind of what this actually means, what does the in-between mean? So when it's not larger than 0 or less than 0, when it is 0, so calculate the temperature at which the Gibbs energy is equal to 0. So when the Gibbs energy, standard Gibbs energy, is equal to 0, so that means our enthalpy of reaction minus T delta R S naught is 0. That means we can solve for T and get that it is the enthalpy of reaction divided by the entropy of reaction. Alright? And if you solve for that, then it will be 3.213. Of course, it's kilojoules, so let's just make it joule for this time. So make it 3 joule per mole reaction. And entropy, and it's 8.7 joule per Kelvin per mole reaction. Alright, and then the value that I get here is 369.31 Kelvin. And that one looks kind of weird, but you can, if you put it into degrees Celsius terms, you get 96 degrees Celsius. And what is 96 degrees Celsius? Is exactly in between 80 and 110 degrees Celsius. Right? It's almost exactly in between them. And that gives us the so-called phase transition temperature, because it's the temperature where the rhombic, it goes for where the rhombic is the stable form to where the monoclinic is the stable form. So meaning it's the temperature where the one switches to the, where the one form switches to the other form. And we know that as the phase transition temperature. It's like the temperature at which water boils is 100 degrees Celsius, because it's the temperature at which water goes from liquid water to water vapor. That's 100 degrees Celsius. Water goes from its stable liquid form, which is stable below 100 degrees Celsius, so like at 80 degrees Celsius, that's the stable form of water. Then at 100 degrees Celsius, water will boil. So that is then hence the phase transition temperature. And then higher than that, there's a new stable form, which is water vapor. And in this case, it's like the monoclinic sulfur. All right. And that is what this example is all about. So this is what its significant is so this is the temperature where the delta G switches from being a reactant favor to a product favoring equilibrium. But physically what it means, it is the phase transition temperature. So meaning literally it's where the system will undergo a phase transition. So your system is not really interested below this temperature. Below this temperature, you'll mainly see the rhombic form. And then at that temperature, you'll start to see an equilibrium. And then higher than that temperature, you'll only encounter the monoclinic form. Just as you would see, for example, liquid water at 80 degrees Celsius. And then you keep on increasing the temperature at 100 degrees Celsius, you start seeing a phase transition. And then above 100 degrees Celsius, you again only encounter one phase, which is water vapor. All right. And that's the significance of this. And that's how the thermodynamics links with your macroscopic observations of that system. All right. Cool. I think it's cool. I think it's very nice. Right. So that is this question. Right, of course, all the words that I said answered the second part of the question. What is the significance of this temperature? It is the phase transition temperature. So you can write that down as your answer. All right, good. Thank you for watching, and I'll see you in the next video.